Okay, thanks very much for the introduction. So, yeah, okay. Well, yeah, I want to talk about this open-close BCU theory on Calabi-Yau geometry. So the motivation of this work comes from something very old. It's a motivation from actually mirror symmetry stuff. It's try to understand the so-called quantum B model. So actually, it's a question arising from string theory in particular. It's a mirror symmetry between so-called A model and B model. And it predicts something very amazing in mathematics. For example, on one side, you get this curve counting theory, Gormitian theory, and the other side, you get this Hodge theory, for example. And when you see, if you count rational curves, you get exactly the structure for the variation Hodge structures. So on the other side, you can do counting higher-genus curves, and you're asking what's the geometry here? And that's a very basic mathematical question. And this is also somehow the same thing as asking what is the geometry of the quantization of the Hodge theory on Calabi-Yau geometry? So that's a precise mathematical question we want to study. On the other side, it's related to a question in string field theory. I'll explain more about this later. But somehow the idea of string theory is that we associate some string field to the element in the Fock space. And in particular, we have a string action, which basically describes the dynamics. So, and Dieberbach actually has a very remarkable structure describing the closed string field theory. It says that the closed string theory is basically described by a string action, this particular one, which usually contains actually infinite number of vertices and also satisfies the so-called B-wave mask equation. That's a very general structure. And usually it's very difficult to solve this one completely in the general context. So we want to know whether we can solve something, in the topological case. Probably it's more related to some mathematical questions. So that's another motivation. Now, from now on, I will focus on this topological string, and in particular, on this topological B model. So here, there's a fundamental breakthrough by Brzezinski, Zakotty, Grigorova. They describe this B model on Calabi-Yau's threefold by a gauge theory. They call this one a Kodawa-Spencer gauge theory. So it's called a Kodawa-Spencer because if you look at this classical geometry of this gauge theory, it is basically describes the deformation of complex structures. Now, at some point, you can view this particular proposal actually as describing the leading cubic vertex of this Dieberbach string action in the topological B model. And you may wonder, whether we can find the full solution of the string field action satisfying the B-wave mask equation. And a couple of years ago, Castello and I found an interesting solution for this topological B model, which somehow extend this Kodawa-Spencer gauge theory to arbitrary Calabi-Yau, and by turning on the descendant and so on, we should solve the mask equation. So I will try to explain a little bit more. And we call this one BCU theory. So roughly speaking, let me say a little bit words about the content of this theory. So, so suppose I mainly work on this compact Calabi-Yau, but it can be more general. And let me applications first. So let's call this one polyvector fields. It's going to be some smooth sections, under holomorphisms valued in these holomorphic polyvectors, all smooth sections. And now, because we're working on Calabi-Yau, we have a natural holomorphic volume form. Then we can identify these polyvectors with differential forms. So I have natural operators like a D bar and D operator. I'm going to call the same operator on this polyvector side, just for convenience. And also, this volume form basically allows us to integrate things like polyvectors by translating this one to a differential form and so on. That's just some basic notations. Now, how to describe our theory? It's basically something like this. The field content of our BCU theory concerns the following data. It's basically the polyvector fields, the one I just mentioned, with one more formal variable, t. This represents actually the gravitational descendants. It's a differential gradient complex. The differential is given by d bar plus t del. So this is going to be our field content. We're going to build up quantum field theory on this data. But I just compare with the original proposal of Kodawa-Spencer. this original BCOE theory for this proposal of this Calabi-Spencer on the Calabi threefold actually has a field content like this with a constant field. So the element here is this particular kernel of the D operator. So at some point, our solution can be viewed as an equivalent extension of this one, because like in mathematics, we know like complex or derived object usually works much better. So you can view this one as a resolution of this element. So that's our field content. Now, what about these action functionals? Now, the interaction part of our action functional is the following. So I'm going to call this one IO interaction BCOE. It's a very simple. It's a trace. Trace means like integrating stuff. This notion is the following. So it has I have to do Taylor expansions of element. Mu is element of the polyvector field with descendant. So when you evaluate elements like here, so suppose you look at a degree k Taylor coefficient. So this one, you combine the descendant by some coefficient, and that's actually the intersection number on the modular space of rational curves. And you combine these polyvectors and wedge them together, and use the trace to integrate. And this becomes a local functional on Calabi-Yau. That's the interaction part. And you see, like actually, this interaction has infinite many terms. If you look at a leading term by like phrasing this descendant, let's set t goes to 0, and the only leading term when n equals 3 contribute, and that becomes the original Calabi-Spencer cube interaction. That's why we say it's an extension. And remarkably, this formula satisfies a version of classical mass equation. I will say a little bit more about this later. So, moreover, like if you look at this, the field content, the leading term without descendant is the dynamical fields. They propagate. But the other stuff are background fields. But actually, they're all important to contribute to this equation, this mass equation. And so that's the classical part. Actually, starting from here, you can start it to do quantization from this classical mass equation to a so-called quantum mass equation. And this can be done in a very rigorous way and carefully using this technique of renormalizations. But I will see. So, so this looks complicated, but I want to show you like this is actually something you can not only interesting, but also you can solve it. And so I'm going to do a very concrete example to give you some feel about what this one looks like. So I'm going to do the simplest Calabi-Yau, compact Calabi-Yau, which is the elliptic curve. So in this case, so it is much simpler. It's one-dimensional Calabi-Yau. And then we can decompose every element here by just forms and one polyvector. I'm going to denote elements here by uk and eta k. You know, there are infinite many terms and infinite many interactions. But for simplicity, we work on a very special background. Actually, it turns out like this background determines everything. So let me phrase this background field by setting this part, the background part to be 0, and this part to be constant. This is a very it's a constant background field. So if you restrict the previous BCOE interaction to this particular easy background, you find like, well, this classical interaction becomes something like this. It's pretty simple. This is a constant background. You can view this one as a coupling constant. And this one is an integral, and the form looks like this. U to the k minus 2 or k plus 2. It's a very, very simple formula in this case. Now you may observe, okay, what's the meaning of this classical mass equation and how to quantize it? This is the answer. Actually, if you try to analyze the mass equation, you find something which is somehow related to integrability. So you see, you can prove that the classical mass equation I just mentioned in before, in this particular background, is basically equivalent to this equation. So this currents, I mean, the commutes with respect to this Poisson structure. This is actually equivalent to the classical mass equation in this background. And now you can just start to do renormalizations and solve quantum mass equations and so on. You will find that like, eventually you can prove that this quantum mass equation in this background somehow is equivalent to something that you can guess naively. I mean, this one quantized to give you some Kyle operators. And this condition just becomes this quantum condition. This operators commute. And this have infinite many commuting operators. And this allows us to solve the quantum mass equation precisely, I mean, in terms of this action functional. So this action basically is the quantum corrected local interaction in this previous constant background. And that's this particular background, but I actually can show that I can solve, if you let this background field to be not only constant, but in general, you can also find the local functional, but the formula is much more complicated. But this is already illustrating. So that's an example. Now you can start to use this one to compute things like compute generating functions and so on. For example, here's a theorem that if you do this, you compute the generating function of this one on this elliptic curve. You find that a generating function actually some kind of almost holomorphic modular form. So it behaves like has a nice modular transformation property, but this one has a very mild anti-holomorphic dependence on tau. Actually, polynomial dependence on 1/, imaginary part of tau. That's what it means by an almost holomorphic modular form. And then there's a nice way of setting like tau bar goes to infinity limit. And if you compute this limit, you find like the generating function becomes something like this. And actually, this is very similar to some calculations like Dijkgraaf did many, many years ago. So you find you compute this one, you find like, well, this exactly, you can show this exactly the same thing as computing higher genus chromatin invariance on the mirror. So this is a mirror theorem. Basically, it's a mirror theorem on higher genus. So basically, you can also view one theorem as a generalization of Dijkgraaf to the full descendant case. So you see, like this concrete example, it really gives you something quite interesting. That's the BCOA theory. Now the next, I want to go to the open part, and I want to see like how to couple this theory to the open string. So here's some guiding principle. Witten told us that actually, if you look at this, the B2 is the open string field theory, and this one should be described by a version of holomorphic Chern-Simons. So for example, if you work Calabi-Yau threefold, say we're going to work on some kind of bundles or value in some Lie algebras, this holomorphic Chern-Simons functional is something like this. It's very similar to Chern-Simons, but in the Calabi-Yau situation, so you have some kind of holomorphic data. With this infinitesimal gauge symmetry, similar to Chern-Simons, and if you look at this critical point of this action functional, you produce like the structures of holomorphic vector bundles. And that's the guiding principle. And this one should describe the open string field theory in the B model. Now, the question is like, how to put these two together? How to couple this holomorphic Chern-Simons with Kodawa-Spencer? The first hint is the following calculation that I did with the Castello. So it's the following. And you start with this holomorphic Chern-Simons. Let's say look at work with some like a general linear group, GLN, and you try to deform this holomorphic Chern-Simons by single trace operators, and consistent with gauge transformation and so on, and also consistent with like n very large. You can show like this deformation is exactly parameterized by this space. And we see like this space is the field content for the BCOA theory. So this means like this is basically the first order deformation. Now, he gives you an example of this deformation. So the deformation looks like, for example, so, let's say this is an example where this polyvector has no descendant. So this is the leading term. A looks like a connection or some general connections that in this BV formalism, we're adding to goals, etc. Now, the first order deformation of this holomorphic Chern-Simons is given by this guy. So you see, like this is a polyvector field. You have it has many like vector field, and this vector field applied to these connections, and you multiply them together, and you get a local functional. And this is the first order deformation of this holomorphic Chern-Simons. This formula can be generalized actually. If you have some descendants, it's actually more complicated. You need to work with some. But there's also a precise formula. Okay. So here's an example of this first order deformation. Now, here's our proposal. So based on this one, we proposed a classical, this is a classical theory, open-closed bimodal interaction by following. So now our input has two components. Mu from this polyvector, that is a closed string sector. A basically is the connection, so it's from the open string sector. I'm going to write down a local functional, local interactions, combining this data. It's given by something like this. So you see like there's actually it's a very expensive formula, but this CNM means like it's a configuring space of the disk with m points on the boundary and m points on the interior. So this is a picture. I draw a disk, and I put my closed string sector inside in the interior, and put this the connection on the boundary. And the way we write down this interaction is the following. So it's actually the same thing as the conservative graph formula for the deformation quantization. But the idea is that first, with this configuration, like we can associate some, for example, every mu is a polyvector, means like it contains many vector fields. So it's a lot of derivations you can do. And you apply this derivation to the boundary, acting on this A's. So in the previous slides, this is roughly what it looked like, but it can be more general. And then you look at how these polyvectors apply to the boundary, and that's a basic structure of this action functional. But you sum over all the possible cases. But the coupling constant is computed by some integrals on this configuring space. For example, for every edge, you associate some one forms on this configuring space, and every descendant, you associate some sun class, and so on. You integrate something, you get the number, and that's how this action functional look like. And that's our proposal for this open-closed string field, open-closed string field theory in the bimodal. So now the key point is that, this action function actually solves the version of classical mass equation. So this is a picture of this equation. So it's an equation like if you apply differential to this interaction, it's contributed from two terms. Like first one is a BV bracket in the open string sector. The other one is a BV bracket in the closed string sector. And that's it. That is the open-closed BV mass equation at the classical level. And mathematically, this theorem is essentially equivalent to conservative formality theorem, and some kind of thickly version by Vivarcha-Kellogg. And actually, this gives you a very concrete, explicit solution of Zivabek's mass equation for this open-closed string field theory in the topological case. So that's something remarkable. But this is like a classical level. We want to quantize this to get this all the higher genus with the boundaries and so on. So when we started to quantize, basically our guiding principle is the quantization to solve this quantum mass equation. And actually, this can be done. So the first step toward understanding the quantization of this open-closed BCV theory is the following local version. So I'm going to work on a piece of Calabi-Yau. Say it's a very trivial Calabi-Yau. We put this open-closed classical interaction on this particular Calabi-Yau, and now we try to do deformations to solve quantum mass equation. So we look at this particular gauge group, like a super gauge group, GLNN, and we will look at some kind of quantization that is consistent with like n goes to infinity. Now, this is a standard like a deformation problem, like you want to solve quantum mass equations, become calculating some gauge anomalies. This gauge anomalies can be computed by some kind of BIST cohomology. So, that's exactly the way we prove the theorem. So we basically started by computing this BIST cohomology, and we show that this gauge anomaly, the vanishing of the gauge anomaly is reduced to calculate some possible one loop level, actually at some kind of annulus diagram. So most of them are canceled, but we need to do some check. And also, it's remarkable that I learned in this story that is dynamics from both the open string and closed string sector. There's the crucial for this anomaly cancellation. Probably that's something familiar to string theory. Okay, so now you see, like we need to analyze the possible annulus anomaly this problem, and we just do it explicitly. So now we compute this annulus anomaly by looking at these Feynman diagrams. And this is an annulus, and you look at this represents certain Feynman diagrams in this open-close data. And you do computations explicitly for all of these diagrams. And it shows that actually these two terms basically canceled out for this gauge anomaly. And that's the annulus anomaly cancellation. So together with the previous comment that this gauge anomaly is reduced to only annulus diagrams, we show that there's no gauge anomaly for the quantization for the whole stuff. And that's how we prove this theorem. Now, any remarks? Actually, the first remark I want to say is a relation between mass equation for the string field action and these integrable hierarchies. You observe something. Actually, you actually observe something more. So, for example, if you can turn down superpotential in this story, get some kind of Lambda-Ginsburg twisted theory. I can show like the closed string sector for this Lambda-Ginsburg twisted theory. Basically, it's equivalent to some very remarkable story in mathematics. It's Saito theory of primitive form. And actually, you can get more. Like you find some natural interpretation of ADE integral hierarchies for some simple singularities. But you might get more. Like you might get some integrable hierarchies beyond ADE, but we haven't explored much about this yet. And also, like you can look at this how, in this case, the open-closed theory is formulated. It's going to be coupled to some category of matrix factorizations. That'll be also very interesting to understand. Also, one of the crucial things, again, is to construct the whole quantization, quantum theory, on arbitrary Calabi-Yau, arbitrary compact Calabi-Yau, probably by gluing our local data and things like that. So I hope to understand this more later. And another thing I want to mention probably is the relation with twisted supergravity. Like Castello and I have a conjecture which roughly says that this kind of Biot theory on C5 probably is equivalent to a twist of type 2B supergravity in 10 dimensions. And we have some hints on this one as well, and probably something more. So there are many interesting things here to explore. So finally, just let me thank you for coming here, and welcome to Tsinghua, and enjoy your stay. You want this or yes?
So the example you mentioned, the context of T2 just gave an example of the post. You had deformation of the usual topological string by the descendants, and you got the Dijkgraaf's equations that you studied, and extensions thereof. So I want to point out, I think the Dijkgraaf's equation actually does arise in the context of usual topological string and Calabi-Yau threefold, when you have elliptic curve as embedded inside Calabi-Yau line bundle, and that's what we studied.
I see.
In the paper with Robert and a couple of their
I
collaborators.
see.
And I suspect the same story is true in the paper on integrable hierarchies. We showed that all these descendants arise inside curves inside the Calabi-Yau.
A couple to the.
So you can actually embed this in the Calabi-Yau threefold. I mean, you didn't get anything new by these parameters other than saying it's part of the threefold story. And in the threefold, we couldn't add anything more. So
I see.
So it felt like integrable extra parameters do not have a natural point. They only arise as non-compact models within the Calabi-Yau.
I see. Thank you for the suggestion. Yeah.
Does this help you actually compute something? In other words, we are stuck with computations even though it's supposed to be quantizable according to you guys.
If, for example, using this Holom's anomaly equation things to.
Well, the actual equation, how do you compute the partition function?
We don't have a general way. I mean, we don't have a very nice way of computing the general function in general yet. So, the curve example is something we know, but in general, for quintic, for example, we still have no way of doing this way explicitly. So, I hope to get more. But here we first, our starting point is to understand how we can construct this guy in some nice way we can understand, and hopefully get more constraint on these generating functions. Yeah.
This deformation you have with your assignments that you introduce, does it introduce new invariants for like knots? If you go to the A model version,
For
you had some other parameters added, the same coupling of the closed string to the open string. Does that introduce new deformations of knots?
I don't think so.
So how does it deform? In other words, there's a mirror for this, right? What does the mirror do for your knot invariants?
Yeah, I'm not sure about this, but we can discuss later. Yeah.
I'm just wondering if you just go to the case of point, what would be the VCOV?
Yes, but then it's like you see like this is a trivial 3 point, but then you see like there's no quantization. But actually, I'm changing a little bit. This quantization is a quantization compatible with a lot of symmetries, like Virasoro symmetries, for example. Then if you impose this condition, then you uniquely solve this like higher vertex. It's the solution of this.
Because we would kind of argue this is like
we really need.
right?
Yeah, the point case, like I really do quantization with compatible with symmetries, so that they get this point case. You just exactly get this tau, like KdV tau functions. Yeah.
I have a question. So in the physical theory, usually when we have anomaly, it's not cancelled, then the theory becomes inconsistent, pathological. It's the non-unitary. And in this case, what goes wrong if the anomaly cancellation is not satisfied?
Yeah. So this. Yeah. Then you have some problems for at quantum level. So.
What kind of problem does arise?
Well, if say like this gauge symmetry breaks down, I mean, at the quantum level, you lose a lot of constraint and so on. Yeah. Or if you don't like gauge symmetry, then.
The gauge symmetry breaks down?
Yeah, that's a gauge anomaly, yeah, basically.
Okay.
Thank you.